In this video on the quantum mechanics of hydrogen atom, we are going to discuss about the parity of eigenfunctions and how do we determine the selection rule. Now, to start with, the parity of eigenfunction is the property which describes the behavior of the eigenfunction when it is inverted about the origin of coordinates. In rectangular coordinates, the inversion about the origin means changing the signs of all the coordinates. So we consider the eigenfunction psi with minus x, minus y, and minus z as a function of the negative coordinates. And that would be equal to, supposedly we have that to be equal to plus of psi x, y, and z. Now this is what we call as even parity. That means even if we change the signs of the coordinate, the value of the eigenfunction as a whole remains unchanged. Conversely, if we have this condition, that is, if we are changing the coordinates negative sign and we end up with a negative eigenfunction with respect to the original coordinates, then this is termed as odd parity. So this is how we define the even and odd parity. Now we can consider an operator which operates on the eigenfunction and inverts it about its origin, and it is called as the parity operator. So this is the parity operator. It's more or less the same as the in symbol we usually have it this to be the same as the momentum operator, but not to be confused over here. We can just give it a tail a bit and then we will say this is a parity operator. So in this case, this is the parity operator which operates on the eigenfunction, and it supposedly has an eigenvalue e times of psi. Now as far as the rule of the parity is concerned, if this parity operator is operated twice, that means if we are getting p square times of psi, then we will be having e square, and this would give the eigenfunction back as far as the definition goes, because even if it's plus even parity or even if it is odd parity, we'll be having the eigenfunction back after operating the parity operator twice. So from that we can say that this would give us e square to be equal to 1, or we can say that e has two values, which is plus or minus 1. So these are the eigenvalues of the parity operator. An eigenfunction having an eigenvalue plus 1 is said to be having an even parity, while having an eigenvalue negative of 1 is said to be of odd parity. Now, a system having an eigenfunction of even parity is said to be in a state of even parity, and that having an odd parity is eigenvalue is said to be in a state of odd parity. As simple as that. Now, we can characterize the different states of a system by their parity. So if we consider the eigenfunction of one electron atom, then the eigenfunctions are described in spherical polar coordinates. Now when we are having the rectangular coordinates to be changing from x to minus x, y to minus y, and z to minus z, the spherical polar coordinates would change. Now they are r, theta, and phi as we know it. They will change in value like this. The r does not change, it remains as such, but pi minus theta is what we get when we change theta, or we do the transition onto the negative coordinate. And then as for phi, we have pi plus phi. So this is how the change is observed in the spherical polar coordinates. Now the one electron angular eigenfunction is shown to have the following properties. That is, if we have theta of theta LML, and then we have pi minus theta is a function of that, then that is equal to minus 1 raised to the power L plus the magnitude of ml. Remember, ml can have either plus L or minus L value, but we will stick to the modulus of it. That means we'll be considering only the value. And then we have theta L ml as a function of theta. And as far as the azimuthal function is concerned, we have phi, and that will be equal to minus 1 raised to the power ml only, phi ml of phi. Thus we have r nl of r, theta, that is the complete eigenfunction over here, L ml, pi minus theta, and then phi ml, pi plus phi, that will be equal to minus 1 raised to the power L plus 2 times of ml mod, because we have both the ml from theta and phi, and then we have r n l of r, theta of theta L ml, and phi ml of phi. So that's more or less the eigenfunction that we had, but here we have the case of the change in the coordinates. Now the parity of one electron atom, therefore the eigenfunction is determined by minus 1 raised to the power L only, because 2m is going to be even every time, so it doesn't really affect the parity as such. So the parity of one electron atom eigenfunctions is determined by the factor minus 1 raised to the power L. The parity is even if the orbital angular momentum quantum number L is even, and the parity is odd if L is odd. This is true for all eigenfunctions of any spherically symmetric potential energy UR. Now in one electron atom we have several degenerate eigenfunctions corresponding to the same eigenvalue, because L will have n number of values. So for the same n we'll have many values for L. Obviously these components differ in parity in spite of them having the same energy value, so therefore we have the degeneracy involved in that. Now as far as the selection rules are concerned, we will now consider a phenomenon where in an electric dipole transition the parity of the state of the atom must change, and from this will be led to the selection rules. Now what about the electric dipole transition? Now any form of transition, as you know, will take place from one state to the other, that is from the ground state to a higher excited state, and an electric dipole will also execute such transition when it is provided with some energy, and that energy usually is in the form of photons. The incoming photons, they carry a certain amount of energy and they provide it to the given electron, or in this case probably an electric dipole. Now electric dipole obviously is composed of positive and negative polarity, equal in magnitude and separated by a short distance. And in the atomic configuration that we see, the electron or the electric dipole would exist in the form and it will depend on the shape of the orbital that we are considering, because as we have seen that the shape of the probability of electric cloud distribution is going to be different for different states. Now it is going to be spherical in the 1s and 2s state, while it is going to be the dumbbell shape that we had considered or we had studied in the previous video in this playlist. Now, because of that distribution, the dipole remains the same in the 1s as well as in the 2s state, the state of the dipole, that is. So that transition is forbidden. How? Well, the incoming photon has a certain electric field associated with it because it's an electromagnetic radiation. So that oscillating electric field that is associated with that incoming photon, that influences this electric dipole, and that is the only possibility that can influence the dipole, because the dipole is influenced by an external field. And so it influences this dipole, and this dipole is set into transition to a higher state. But the dipole must change in to a certain extent for that transition to occur. It cannot stay the same, which is the case of 1s and 2s orbitals, because they are spherically symmetric. So the charge distribution is more or less the same in both the cases. So we will see a mathematical approach to that, to our explanation. Well, let's see. Here we are stating that the parity of the state of the atom must change, which means in S state the parity is going to be L is equal to 0. It is going to be the same in the S state. From the S to the P state, it can be made possible, because in the P state L is equal to 1, and that is allowing such a transition. That means the final state must have a different parity to that of the initial state. So let's check it. So we are considering the matrix element of the X component of the electric dipole moment. So we are taking the matrix element, let us say we are taking it as Rx final with respect to the initial, and that is equal to, that is given by the final state eigenfunction, and then we have the electric dipole in case of the X component of the electric dipole, and this is the initial state, and all of it is considered along the X component or the X coordinate. So these psi f and psi I are the final and the initial states of the electron, and or of the configuration, you can say. The parity of this factor, that is E times of, that is the charge times of the distance, that is going to be odd, because we are going to have E times of minus xj, and that is going to be equal to minus of E times of xj, because when we are changing the coordinates, changing the sign of the coordinates upon parity operation, that's going to change the sign of the rectangular coordinates, as we have discussed earlier over here, right in the very beginning of this discussion. So therefore that is going to change. Now, if the initial and final eigenfunctions, that is psi I and psi f, if they have the same parity, either both being even or both being odd, the entire integrand will have an odd parity. And as a result of that, when we are considering the contributions from the volume elements that are involved, that is in this case probably if we can consider the P subshell, where the upper lobe and the lower lobe are involved, one of the volume element will cancel out the contribution from the diametrically opposite volume element, and as a result of that, because there is a change in parity, and as a result of that, the net result is going to be a 0. And that's exactly what I have mentioned here in writing, and that would lead to the integral being 0, so which means the transition rate will be 0, and that follows for the y and the z components as well. So for the electric dipole transition to take place, the parity of the final state eigenfunction, that is psi f, must be different from the initial state eigenfunction. That is, the parity must change. So if we have the parity to be odd in case of this coordinate transition that we saw at the very bottom of the screen that you're seeing right now, this, when multiplied to that change in parity that occurs between the initial and the final state, that would result in a positive parity, and hence we'll obtain a certain transition rate of some finite value. So that's what we were discussing, that the parity of the final with respect to the initial psi, that is the state, that must change in order that the transition occurs. A simple case being that what I had discussed earlier, that we have a spherical charge distribution where the polarity is where the probability of finding the electron is in that spherical cloud, and we cannot have a transition to the from that 1s cloud to the 2s cloud because the polarity is going to be the same. There won't be any form of transition occurring, and that's not possible because the dipole must this would mean, if this transition takes place, this would mean that the dipole hasn't really interacted with the external incoming photon, which would have impacted the orientation in the dipole. So this is not really possible. However, if we are considering the other state, which is the dumbbell shape charge distribution, probability of having the electron, then in that case there is a difference in the charge probability charge distribution, and as a result of that there is a change in the polarity, or there is a transition that can be possible from the S state to the P state. Now similarly, from the P state to the D state is possible, but not otherwise, that is from the S state to the D state, that is not possible, because in that case again the parity will be the same, because L being 0 in the S state, L being 2 in the D state, that is also an even parity. So the parity is determined, as we have already discussed, by the -1 raised to the power L rule, the transitions corresponding to delta L being equal to 0, plus minus 2, plus minus 4, and so on, they are not allowed. However, these are even parities. The initial and the final eigenfunctions would have the same parity in this case, so that is not possible. The transitions are, however, allowed for del L to be equal to plus minus of 1, plus minus of 3, plus minus of 5, and so on. But we still have another case, where a case from the correspondence principle and the quantum mechanical treatment, we have del M as the selection rule that allows is that del M must have 0 or plus minus 1 as its value, and this is another selection rule. We'll be discussing it in detail later. This will be coming out in the Z-man effect. So this, because the magnetic dipole moment that we are considering, that is due to the influence of the external magnetic field, so that is another case to be discussed later during the Z-man effect. So this rule disallows for del L to be equal to plus minus of 3, plus minus of 5, and so on, that is higher than plus minus of 1, because that would have del M to be greater than 1. So Finally, we end up with a selection rule del L to be equal to plus minus of 1. This is the selection rule that we have for L. The electric dipole selection rule is therefore del L is equal to plus minus 1. This is, however, not, this does not, however, prohibit the transition which violate this rule. There are also transitions which will violate this rule that have been observed, like in case of the oscillating magnetic dipole moment or the oscillating electric quadrupole moment. But the probability of such transitions is very unlikely. The transitions which have been disallowed have occurred, so there's no rule which completely obstructs them or denies such transition. But the probability of such occurrences is very, very, very less and very unlikely. So this is what we were to discuss about the selection rule and the case of parity. So we are done with this quantum mechanical case of the hydrogen atom. We'll be discussing a few numerical value problems for clarity on the topic, and that is in the upcoming video, and thereafter we'll be moving on to the topics further in the molecular and atomic spectra. Till then, thank you for watching.